Last time we talked about graph isomorphism. We saw the definition, and then we saw an equivalent definition in terms of something else, which was called graph homomorphisms. Now, it's easy to start to get these mixed up, but remember, isomorphism is going to be like isomorphism of sets or isomorphism of other things you've seen that have isomorphism, like maybe groups, maybe vector spaces, where the homomorphisms are really just our functions between graphs. And we define them really to be this way, to be functions, that is, homomorphism between a graph G and a graph H was a pair of functions, a function from the vertex set to the vertex set and the edge set to the edge set. And we had this requirement that the map on the edges, that function on edges, had to really be kind of induced by the function on the vertices, that the mapping on the edge AB would just map it to, say, f of A, f of B, where f is the function on the vertices. So we have now a notion of functions or homomorphisms between graphs, and we use that to define isomorphism of graphs, which is going to be our main notion of equivalence between two graphs. And today, we're going to see how we use that notion of equivalence to define an important, very, very, very important idea, which is graph invariance. And a graph invariant doesn't help us if we want to answer the following question, right? If we want to know, if I have two graphs and I ask, well, are they isomorphic? It's a natural question to ask, but really what we're going to get from a graph invariant is to be able to answer the question, how to tell if they're not isomorphic. Okay, so that is to be able to tell two things apart. So if they're not isomorphic, remember that to be isomorphic means that isomorphism exists. So to be not isomorphic means, in other words, no isomorphism exists between the two graphs. Now, if I wanted to show you that two graphs were isomorphic, if I want to prove it to you, one thing I could do is I could give you the isomorphism. Because I want to prove that an isomorphism exists. If I give you one, then you'll have it. You can check, or we can check together, that it really is an isomorphism. And then you've shown that the two graphs are isomorphic. You've shown that it satisfies the definition. If I have two graphs that are not isomorphic, and I want to tell you, I want to prove to you, I won't just assert it, I want to prove to you that they're not isomorphic, then I need some better tool, something else to argue that point. Like a really bad answer would be, let's put the bad answer. The bad answer would be what? Well, I looked for a long time. I tried really hard and I couldn't find one. You know, I looked, but didn't find it. Now, it might just be you didn't look in the right places. Like maybe you can show that you looked at all possible bijections between the vertex sets. But, you know, there are a lot of bijections between vertex sets, especially as the number of vertices gets large. If there's n vertices in each graph, you're looking at something like what? Is it n factorial different bijections? It's kind of a lot. So we don't want to do that. What can we do that's better? There's certain obvious things that work, right? Let's try some obvious things. Like if you just see that the vertex sets have different sizes, then there's no way there's a bijection between them, right? So if the size of the vertex set in G is not equal to the size of the vertex set of H, then G can't be isomorphic to H. This is not possible, right? Because there just won't exist a bijection on the vertex sets. Similarly, if the number of edges is different, like if the edges in G is a different number of edges in G as in H, then again, G cannot be isomorphic to H. Right? So this would be a clear signal that the two graphs are not isomorphic just by having a different number of vertices and edges. And I just asserted that here, but you can prove it. Right? Let's do that. Let's just see how we can use the definition of isomorphism to prove that these two conditions would be sufficient to show that the graphs are not isomorphic. All right, so suppose G is isomorphic to H. Okay, so I'm going to prove the contrapositive of these two statements. I'm going to do the contrapositive of both at once. So suppose they are isomorphic, then by definition, we've got some F, which is going to be isomorphism between them. So it's a pair of functions, right? Because every isomorphism is a homomorphism, right? It's going to map G to H. It has to be the case that the function on the vertex set and this function on the edge set are bijections. But if these are bijections, right, and the edge set and the vertex set, these are finite sets, so bijections don't change the cardinality, so this implies immediately that size of VG is equal to the size of VH, and similarly, the size of EG is equal to the size of EH, right? And again, this is because FV, I'll just write it out for V, it'll be the same for H. FV maps VG to VH, and whenever you have a function, which is a bijection, then bijection between finite sets here, their cardinalities are the same, right? The sizes of the sets are the same. Similarly for FE and the edge sets. Okay, so this was kind of, I think, the obvious way to see that two graphs are clearly not isomorphic. But just because it's obvious, it doesn't mean we don't actually work it through the definition to see that this really is true. So what we've really shown here is that VG, the size of the vertex set, and the size of EG are unchanged by an isomorphism. So any isomorphism that I use between G and any other graph, the new graph will have the same size vertex set and the same size edge set. And so really what these are what we would call graph invariants, right? So it's any property of a graph that's unchanged by isomorphism. Now this is we have to be a little careful here. This is a bit of a loaded word because, well, it's not even that it's a loaded word, it's an unloaded word. It's a word that we didn't really say what we mean by a property. So for now, you should think of a property as any kind of function that goes from graphs to, I don't know, something with a notion of equality, so that we can actually tell if something changed or not. So it has to have some notion of equality or isomorphism on this side. Otherwise, we wouldn't be able to tell if it was unchanged or not. Okay, and in this case, the size of the vertex set is a function from any graph to integers. And the size of the edge set, again, is a function from graphs to integers. Not all of our graph invariants will map to integers like this, but these simple ones do. Okay, so now let's try to work through a real example. Here are two graphs. And my question to you is, are they isomorphic or not? And if they're not isomorphic, why? How would you prove that, in this case, there either is or is not an isomorphism between them? If you don't want me to spoil it for you right away, you might want to pause the video and think about it. Otherwise, well, here's the answer. They are not isomorphic. But the two invariants we've seen so far are certainly not sufficient for us to prove that they're not isomorphic. Because if you count, you see, wait, 5 vertices, 5 vertices. 1, 2, 3, 4, 5 edges, 5 edges. Okay, so same number of vertices, same number of edges, but they're not isomorphic. There's no way for me to have a bijection between the vertices in G and the vertices in H that also induces a bijection on the edge sets. So if you think about this a little bit, and again, you might want to pause and think for, like, in what way could you show that there must be non-isomorphic? I think the answer that most of you would probably come up with is something along the following lines. You probably observe something like, well, G has only one vertex of degree 1 and H has 2 vertices of degree 1. Or you might have noticed that G has 1 vertex of degree 3, and H has 2 vertices of degree 3. And it seems like if they're isomorphic, then the degree should be unchanged. So let's just check. Is that really correct? The claim is that if G, if I have a G here, or F is going to be my isomorphism. So if G and H are isomorphic, let's indicate it like this. So F is the isomorphism that takes me from G to H, and I just marked it as an isomorphism. Then it should be the case that the degree, let me write it like this, the degree of a vertex U should be equal to the degree of FV of U. All right, so wherever F maps that vertex U, it should have the same degree on the other side. So this is the degree in G, this is the degree in H. This one, you can prove it. I'll leave that as a little exercise. It's very easy to do. And you see that if this is the case, then if you wrote out all the degrees in the graph, so if I took all the degrees in G, and maybe we'll sort them. So there's a vertex of degree 1, then there's a vertex of degree 2, and then there's 2 more vertices of degree 2, and a vertex of degree 3. And similarly now, if I looked at the degrees in the graph H, I would see, okay, well, there's a degree 1, a degree 2, and then 2 degree 3 vertices. So any bijection between the vertex sets would give me a bijection between these where they have to, 1 would have to map to a 1, a 2 would have to map to a 2. And there's just no way to do it. See, there's only 1, 1 up here, and there's 2 down here. There's only 1, 3 up here, and there's 2 down here. So there's just no way to have a bijection that will satisfy this fact about isomorphisms. So right there we get a proof that these 2 particular graphs are not isomorphic. But we also get a new invariant. You see this sequence, this degree sequence, it's sometimes called the score. So it's a sorted list of numbers, which is the list of degrees. If they're different, then the graphs are not isomorphic, which is exactly, remember, this was what we meant by a graph invariant. If we had an isomorphism, then this degree sequence would not change. That's exactly the definition of a graph invariant. Okay, so we have another graph invariant then, this sequence of degrees. At this point, we should note something really important, which is implicit in the definition, but it's something that I haven't said out loud, or even if I hinted at it, this is the most common mistake when first starting to look at graph invariants, is people forget this important fact, that the graph invariant gives you necessary but not sufficient conditions for isomorphism. That is, if the invariants come out the same, well, that's necessary for being isomorphic, but it's not sufficient. And really simple example, take this graph here, and another one that also has 6 vertices, 6 edges, and a degree sequence of 2, 2, 2, 2, 2, 2. I think I got the right number of 2s there. Right, so of all the invariants we have so far, these 2 match, but they're not isomorphic. And you can come up with some other, you might even discover some new invariants here. It seems like this is somehow 2 pieces over here, and this is 1 piece over here. It seems like that should be an invariant. We'll prove it is. So just having the same invariants, no matter what invariant you pick, having the same invariant is not enough to actually be isomorphic. You can imagine a kind of perfect invariant, which is like, maybe there's a number for every graph, and if you check if the number comes out the same, then the 2 graphs are isomorphic. But I don't think we know of any that are, at least any that are easy to compute. Okay, so don't forget this fact. Necessary, but not sufficient. Okay, let's do another example. All right, here's two more graphs. Oh, okay, we've got it harder now because we've got more vertices. We've got up to 6 vertices. We're really taking on the big ones now. If you want to pause it and think real hard about this, see if you could untangle these to look the same or not, and then when you come back, I'll spill the beans. The answer is that these again are not isomorphic. Okay, so I've got 2 distinct graphs. I think if I were to look at the invariants I have so far, the vertices, edges, degree sequences are all the same. 6 vertices, 7 edges, degree sequence of 4 degree 2 vertices and 2 degree 3 vertices. Even the other invariant that I hinted at about having the same number of pieces is the same. They're both 1 piece. So now we have to look harder. We have to think more about what could be different about these 2 graphs. And if you pause it and work on this a bit, I'll bet you'll find some things that are different in a way that matters. It matters enough to guarantee that there can't be an isomorphism. So a couple possibilities that you might have come up with. One of them may be, given if you still had our last couple lectures in mind, you might have noticed that G is bipartite. That's a property of the graph. And H is not bipartite. You can check that just by seeing that, well, it has odd cycles. And if you have a triangle, there's no way you can be bipartite. And so you might have also picked out this one, right? G has no triangles. Did you notice that? It must not have a triangle because it's bipartite. These 2 are almost the same, but they're different statements about the graph, so let's write them separately. Has no triangles. I'll just write them as K3 because that's really what the subgraph is. H has K3 subgraph. So here, both of these are sufficient to prove that these are not isomorphic. All right, that these differences, both of these differences matter when it comes to isomorphism. And in other words, both of these statements about these graphs are invariants of the graph. That any graph isomorphic to G will also be bipartite, and any graph isomorphic to G will also have no K3s. And so let's prove these. So it's really 2 different statements. Let's just start with the first one about bipartiteness. When we talked about homomorphisms, we saw that G is bipartite if and only if there exists some, what was it? It was a morphism from G to the complete graph on 2 vertices. So there had to exist this morphism to be bipartite. And now we see, well, if we have the isomorphism between these, then we have an isomorphism, let's call it F, from H to G. And that is an isomorphism. In fact, it doesn't even have to, if we had any morphism from H to G, then we could compose it with C. That is, we could take C composed with F, would give us a homomorphism from H to K2, which would be true if and only if H is bipartite. Okay, but it's not, so we know they're not isomorphic. In other words, we see that if we have an isomorphism between graphs where one of the graphs is bipartite, then the other one is also bipartite. So this is us proving that being bipartite is a graph invariant. Let's check the one about having no triangles. I think I have another copy of this graph here. Let's hope so. Yes, good. All right, here's G and H again. In this case, we want to show that if one of them has no triangles, then the other has no triangles. Or equivalently, if one of them has a triangle, then the other one also has to have a triangle. That's the easier one to do, right? So H has a K3 subgraph, so K3 is a subgraph of H. And here, of course, we also really just mean that there's a graph, a subgraph of H, which is isomorphic to K3. A nicer way to write that is that there's some homomorphism from K3 into H. Actually, it's an injective homomorphism, but that doesn't even matter for us right now. Actually, any homomorphism from K3, from a complete graph into another graph, is going to be injective. We'll do that one as an exercise as well. For now, I have this homomorphism, right? It says that there's some way to map a triangle into this graph. And you could pick actually two different ways of doing it, but I'll just pick one of them. Again, now, if they happen to be isomorphic, that is, if I had some isomorphism F that mapped H to G, then the composition of these, right, I'm going to compose them in the other order now. That is, if I took F composed with I, right, that means I'm going to go from K3 to H, and then from H into G. It gives me a mapping, that is a homomorphism, from K3 to G. Right, so it means that H had a triangle, H had this K3 subgraph, and if they're isomorphic, then G would also have that subgraph. This is saying that K3 is in G. Now, if this wasn't K3, if this was just some other subgraph, we could actually make this proof work as well. We would just have to observe that the isomorphism has to be injective and the composition would also be injective, and so it would have that subgraph as well. But in this case, since we check that G has no triangles, then we would get a contradiction. So this would imply a contradiction, and we would conclude that in fact there is no such isomorphism, right? Because this is the whole point of these invariants, is that it gives us a way to prove the non-existence of an isomorphism. So those are the basic examples. Let's just recap real quick here. So we saw a bunch of different graph invariants. We saw a number of vertices, number of edges, the degree sequence, whether or not it's bipartite, whether or not it has a triangle. Each of these gives you possibly a quick check to see if two graphs are isomorphic or not. Checking if it has a triangle is probably one of the more expensive of these operations. Still not so bad. But either any one of these, if you compute the invariant and you compare the invariance between the two graphs, then if they're different, then you know that they're not isomorphic. The setup is almost always the same. I have G and H, and I want to know, is this true? So I turn to my invariant, whatever it might be. I have some invariant of G and some invariant of H. And if it comes out that they're not equal, then I know I am not isomorphic. If it comes out that they are equal, I actually don't get any information. It helps me not at all. So if I compute the invariants and they're the same, I really don't learn much. But if I compute the invariants and they're different, then I know that they're not isomorphic.